Hello again, folks. This video is primarily for my MAT-114 students, in which case the section number for this topic, graphing linear equations, would be 6.6. That's basically what our schedule is at this point. I put this over here where you see it in red, MAT-114, just because it coincidentally happens to be the exact same material. So rather than shoot two videos to discuss the same topic, I'm going to kind of try to do 2 for 1. For you regular MAT-114 people, I want to make one modification to the calendar. All right, here's our schedule. Today we should be doing section 6.6 and 6.7, but in looking at the material, it's kind of a lot to assimilate all at once, so I figured it probably would be better to do 6.7 on the 30th. All right, so I'm going to push that to Wednesday, and the material that was on Wednesday, section 6.9, I'm going to attempt to do on Friday instead. That way it doesn't mess up the schedule next week, October here. Okay, for those of you folks who are here for some intermediate algebra 090 support, it is, again, it's the identical material. All right, and the materials that I have in Canvas will be available for you. Let's see, put that away. The packet that I have prepared for 114 and 190 will be similar. Looks like this. First of all, you have a coordinate plane. And let's see, there's this overview that I had made a while ago. This is a basic summary of different methods of graphing linear equations. Actually, this method here would graph, something even more complicated. If you had a quadratic equation, you could employ this. It's the most brute force of all methods. It's generating your own dots, basically. These two methods in the middle, and we'll discuss all of these in depth, are the go-to method, really more so this one, slope-intercept form of equation of a line, that works exclusively for linear equations, right? And this, if you were in a class that required a graphing calculator, of course a graphing calculator is, so you could think of it as a method, right? It's literally press this button and then press this button and then enter the equation as you see it, and it will graph, all right? That's cool, right? For you folks that are in 114, you're not required to have a graphing calculator. You're only required to have basically a scientific calculator, which is like a $10 to $20 calculator by comparison. Notice the screen much smaller. For those of you folks in 090, you would be using a graphing calculator, right? And I'm going to explain this to the rest of the class as we go through it, right, when the time comes. All right, so this is just an overview. All right, to be a little bit more specific, all right, to discuss this method, the most brute force method generating your own coordinates, I enlarged the table so you could use that as we go through. And this method just reinforces X-intercept, Y-intercept method. If you're graphing a straight line, you only need 2 dots, basically. So if you use the number 0 in different places in the equation, you can get it to produce 2 coordinates, 2 sets of coordinates, ordered pairs. Right, so that's just a larger thing. Here's another table. This is overkill, but if you want some scaffolding while you're writing. Here is the third method, also as a table. Y-intercept method is more or less the go-to method if you're doing it by hand. You should try to, all right, especially you 114 folks. And then for people in 114, also here's a word problem that we'll be discussing. Okay, so try to print that, and then we'll go through this. Let me put that aside. Okay, put my eyeballs on here. All right. Yeah, cheap special effects. I have this giant Publishers Clearinghouse check for you all, I use this to draw on. You win the prize. You win a math class. Yay. That go there. hopefully it doesn't fall over. Alright. And if the sunlight is a little too intense, let me see if I can, no, that doesn't help too much. Oh, brother. Let me erase this. And I'll try to deal with the light. Sunlight is a wonderful blessing to work in. I would hate to be in an office building that didn't have windows, and I have. It's terrible. But it's kind of a nuisance right now. So, I gotta figure something else out. I'm not sure if the light is coming from where. Alright. Appears to be coming from there. I'm gonna see if I can get a sheet. Alright. Maybe I'll tack it up. And if not, I'll just make do. Just like a regular classroom, right? Although I wish I had blinds. Alright, let's see if this works. How badly that is. Get out of the way. It's a bit dark. There are limitations to what I'm going to be able to do here. I think I had better not. Sorry. Technical difficulties. Alright. Anyhow, take out that paper. Take out this paper. I'm just going to use this for the sake of labeling and such. Alright, first of all, although I didn't do that, I'm going to draw some axes here. Hopefully you can get away with this. Alright. The page that you have is naturally already drawn, the horizontal axis, but I have to finagle it here. Hopefully that's not too faint. It's like my black is fading out, so I'm going to have to get new markers, but we'll see. It's just visible. Let's see how this one does. That's better. Geez, I'm going to do something to begin with. I'm going to do some time in the cup over there. And I'll put this way. See that my board here is a little off kilter, but it'll have to do. There we go. Alright. And just dull it down a little bit. Curious, when you draw on the marker, it erases itself. That will be sufficient. You don't need one of these, I hope. Unless you have some sheetrock that you have to deal with. Alright. Just to get the terminology out of the way, this is referred to as a Cartesian coordinate plane. And it's named after Rene Descartes. curious, is Rene Descartes, which I believe I'm spelling correctly, who lived between 1596 and 1650. I only mention these dates because to give you a feel for when this first occurred, all right? That does help when you're trying to understand something. You begin to realize the limitations of the time frame. All right, if you're talking about the 1500s to 1600s, all right, the printing press is maybe, I'm overestimating probably, but about 100 years old. All right, so this was a revolution in thought. All right, the idea that you could locate something, all right, by superimposing a grid onto it. All right, anyhow, because of the time period also, Rene Descartes was a French fellow, all right, they use a little bit of Roman numerals still, all right, so like when referring to a particular section of the coordinate plane, it's labeled in Roman numeral I, all right, this is referred to as a quadrant, and we read weirdly sort of counterclockwise. If this is quadrant 1, then this would be quadrant 2, and this would be quadrant 3, and this would be quadrant 4. Think of it like Rocky movies. Rocky 1, Rocky 2, Rocky 3, Rocky 4. That is an I and then a V. This is subtraction. Okay. The horizontal axis, which runs this way, is specifically the x-axis. And the vertical axis is the y-axis. Where they cross, right, is the most important point right here. This is the origin. Origin, some people say, same difference. And it is the point, the location 0, 0, meaning that it is neither left nor right, and nor is it up nor down. It is dead center. It's the point of reference from which any other point is located. It uses this as a frame of reference, a reference point. Okay. These are referred to whenever you see parentheses, a number, a comma, a second number, close parentheses. These are officially an ordered pair. In algebra, it's usually strictly two-dimensional, so you'll have an x dimension. It's the number that's written first. X is first. And then the comma, and then the y dimension, which is second. And when you are trying to draw a point, you have to convince yourself you always do the x first and you do the y second, as long as you're talking about a coordinate, an ordered pair, a set of coordinates. All right, so just say hypothetically, if you wanted to plot, right, 2, 3, right, you would always, it is implied, it is understood that this is an x and this is a y. You go to the origin and you count over 2 increments, resist the temptation to actually make a mark at this point until after you've gone the y amount. And then you go up 3, 1, 2, 3. You would place a dot there. That's this point specifically. All of this in reference to the origin. Right. As for the quadrants, right, in terms of what the signs would be for the x's and the y's. In quadrant 1, you could expect that they'll both be positive. Right? The x will be positive, the y will be positive. In quadrant 2, x's will be negative and y's will still be positive. In quadrant 3, they'll both be negative. And in quadrant 4, be positive x and negative y. Okay. Incidentally, Rene Descartes is also famous for that expression, I think, therefore I am. He was a philosopher. Okay. So I always thought that was interesting. I couldn't do it any justice, you know. It was a proof of that you exist if you think all right, then you must be an existing thing, an existing being. You should ask a philosophy person about that. But I think, therefore, I am. That's one thing René Descartes is known for, and also the mathematical coordinate plane here. All right. Now, that's pretty much the terminology that you would need to know. Let me do an example with you, and then we'll graph it after the fact. I don't want to mess this up too much, because then I'll have to draw it again, but let's see. Let me see if I can get away with swapping this out. I have another piece of acrylic plastic. It's cracked, unfortunately, but it is almost the same size. So maybe I'll just do that. I think I'm just fighting an uphill battle here. Let me just erase this. While you're waiting for me, why not take out that larger table that says input output, and I'll give you an example for that. I don't have a projector, unfortunately, so I can't project what I would have liked to. If we were in a regular classroom, this page that looks like this, I would have projected onto a whiteboard or something. And here's the enlarged view of the same thing. All right, this is one of the three methods for basically drawing a linear equation. So we're just going to try to simulate it the old-fashioned way. All right. Let's just call this method 1. Right, for graphing. Brute force. Brute force is not always the best choice. The name indicates anything, but it works. As a matter of fact, brute force, the most basic way to graph a linear equation, is a good way to get your feet wet, to get a feel, right, for what's actually happening. Basically, you create your own dots. So if you have an input, and I'll just draw a line like this, and then you have the equation that you're working on. If you follow the order of operations, you can get it to spit out an ordered pair. Now you might wonder, geez, that faded out real quick. I'm going to put this on. If you're wondering why these particular numbers to use to generate coordinates, that is -2, -1, 0, 1, and 2. It's for no reason other than that they are small. They're warm, fuzzy, and unfamiliar. 0 is a super easy number to use, right? Because it really has almost no bearing on the rest of the equation, right? If you add or subtract 0, it doesn't change anything. If you multiply by 0, it cancels out, right, that term, right? The only thing that you can't do is divide by 0. You could divide into 0, but you can't divide by it. Right? It would be undefined. Right? Anyhow, to use these numbers strategically, -2, -1, 0, 1, and 2 would be practical. All right, and I would again suggest if you have to do something even more complicated than a linear equation, right? Say you were graphing a quadratic and you had no idea how to draw it, generate your own dots. Right? Another practical thing about this is that it gives you a nice even spread of negatives and positives. Right? So you flesh out the skeleton a little bit more the more dots you generate. It's tedious, but it's not difficult. It just takes long. Right? Anyhow, here's an example of an equation that you might use to illustrate. Y equals, and then you have something like this, 2x plus 2. Right? This, first of all, can be identified as a linear equation because if you analyze the degree of the variable x, and it would most often not, no one would bother writing it, it's understood as being degree 1. If you have a degree 1 linear equation, right, you can expect a straight line. If you have something more interesting like an exponent of 2, you have that parabola shape, sort of a hybrid of a U and a V, but it's neither of those. Kind of just bears a resemblance. All right. When I do this, I put a little pocket, parentheses, where the variable was. So I'll do that several times. And then fill in that pocket with the numeral that I've chosen for my input. Let's see if this works. Does that help a little bit? Okay, the sun is starting to go behind the building here. All right, so let's say that in place of x, I put -2 in this case. In place of x, I put -1, 0, 1, and 2. You should follow the order of operations. When you're doing this. That is when you're calculating. And the reason is because you're not, I know it's an equation because it has an equal sign in it, but you're not solving the equation, all right? Well, you're solving for y, technically that's true, right? But you're just sticking with one side. That is, there's no rearranging, there's no moving stuff over equals. So you don't have to really employ algebra so much as you have to employ arithmetic. Which is good news because it means what you see is what you get. It says add, then you're going to add, right? Depending upon the combinations of the signs. Right? You don't have to do opposite operations is what I'm getting at. And if you're following the order of operations to simplify these sides strictly, you do the multiplication first. All right? So 2 times -2 is -4. All right? One of each sign dictates that you subtract according to the rules for integers for adding and subtracting. So that will establish a digit of 2, because 4 minus 2 would be 2. And then the sign of this would match the larger one of these. So larger magnitude. The negative technically has a larger magnitude. That's its distance from 0. Its absolute value. This would be -2. Now, if this is what you used as an input, and this is your machine, and you do this work, right? It spits out this output, which I have mislabeled here. Output. There's a little bit more pronounced here. Input, output. Input, output. This is your machine, if you will. Give it something, do the work, spits out something. Right? -2, -2. Right, that's your first dot. All right. Then you would do the same thing several times. All right. So feet appropriately wet. We follow the order of operations again. Do the multiplication first, then do the adding. 2 times -1 is -2. One of each sign you subtract. That establishes 0. 0 is not a negative or a positive. It's exactly in between. So in tandem, what you used and what you got, right, is -1, 0. This one again, 0, very easy to use. Cancels out this term. You're just left with 2 plus 2. 0, 2 is your coordinate, or ordered pair, I should say. 2 times positive 1 is 2. Same signs, you add them. 2 and 2 is 4. So you have 1 and 4. The positive is superfluous. You don't have to write that. Right. I often do if I have a negative somewhere in it. 2 times 2 is 4. Positive 4 really. Same signs, add them. This is positive 6. And then your ordered pair is 2 and then 6. Hopefully that's in frame. That's a little bit out. There you go. Okay. All right. Again, to stress this, right? This is the most basic method. It's truly brute force because you're doing the calculation by hand, and it's kind of overkill. You don't need 5 dots to draw a line. You need 2 minimally. All right. But the more that you generate, the more coordinates, ordered pairs that you create in this process. You could just use all the numbers, -3, +3. In theory, you could use the numbers in between 0.5 or 1.5. The more that you do, the more that you flesh out the picture. All right? That's the advantage to doing it a lot. Anyhow, let's see what the picture would look like. I unfortunately do have to erase this, but let me kind of cheat for a moment. I'll put this aside. I should invest in more plexiglass here. And I'll put my plane back here. That's just sufficient enough. It's the same exact size. Very good. Anyway, that was the piece of acrylic that I had used at the end of last semester. All right. I do have to do this again. So very quickly. Sometimes it's better to do things freehand. Oh God! Stop making that noise. Okay. That's good enough. Okay, here's our coordinate plane. Alright. And to draw this picture, I'm going to basically use these coordinates that I've generated to draw a line. I really should not move that around. It breaks very easily. -2, -2. All right, remember, as long as you're working with a true ordered pair, and that's something that seems very similar, when you're plotting coordinates, you always start at the origin. So from 0, 0, where the line, the axes cross. All right, -2 is this way, 1, 2, and -2 is down. Again, resist the temptation to actually make a dot until after you've moved the Y around. Okay, back at the origin, all right, -1, and then if it's 0, it's neither up nor down, so you stay put. All right. Back at the origin, if it's 0, it's neither left nor right, in this case, because it's an X, and +2 is up, so you will put a dot here. Before I finish, let me just make a point as well. When you're doing this, you can kind of tell whether you did your calculation correctly or not. Because if you start to see a pattern forming, right? If it's a straight line, then they should be in a line, all right? The phrase would be, the points should be collinear. Which basically means aligned. All right? If you get some stray dot, it probably means that you fudged the calculation somehow. All right. No sin in that, but you make the correction and you catch yourself. All right. Back at the origin, positive 1 is over to the right 1, and then up 4. 1, 2, 3, 4. You have a dot here. All right. And then the last one was I did 5 points from the origin. 1, 2, and then up 6. 1, 2, 3, 4, 5, 6. All right. Now notice something. I could now, seeing this this obvious pattern here, connect the dots. I wish I had a better ruler. Use this. I have a closet here filled with my tools and stuff. All right. What you should do is, unless there's some other instruction saying that these are discrete points, and they're not. You could assume that they're not unless they specify. You should draw a line through them, right? Connecting them indeed, like you're drawing a picture from when a kid, I'm going to place mats in a diner, all right, connect the dots, kid. You know, tons of fun waiting for your pancakes. Overextend the line, all right? Draw an arrow on it to indicate that it goes into infinity this way, and an arrow this way to indicate infinity this way. Basically, a line is just a bunch of dots that are touching, right? These particular points are exaggerated because these are the ones that I actually bothered to do the calculation for. Let me just point to it here. All right, here's my own example of the table filled in. All right. In theory, it would be a little bit more difficult just because of the nature of the numbers involved. You could have done the calculation for what would have been not just 1, but what exists in between 0 and 1. That is to say, you could do a calculation for 0.5, right? Otherwise known as a half. If you inserted a half into the same equation, 2x minus, 2x plus 2, right? It would have told you where this would be, right? Here's proof. If I stuck a half in here, the fraction form of this instead of 0.5 would actually be advantageous. It would be a little bit easier. Why? Because it'd be a cancellation effect, right? And you'd just be left with 1 plus 2, which is 3. Which means that this coordinate at 1/2, the y value would be 3. Let's see if that's correct. If that's 1/2, go up 3 spaces. 1, 2, 3. Are you on the line? Indeed. Right. What's the whole point of any of this? All right. Basically, something that is two variable linear relationship like this can be used in science experiments to make predictions. All right. You don't have to have all of the data, but if you have a lot of data to begin with, you could make a prediction about some data point that is beyond your experiment. They call that extrapolating. If you wanted to figure out a piece of data that is somewhere in between your data points that you have established, that would be called interpolating. So it has a practical usage, typically in business and in science. All right, as long as it's two variable, right? It doesn't have to be called X and Y. Very often it's called something else. Okay. Anyhow, anything that is degree 1 like this, the equation was 2x plus 2, and degree 1 implies that the exponent here is no worse than the number 1, and often we don't bother to write it. You can expect a straight line, right? Which is why this is referred to as a linear equation. It's a straight line. The relationship between this variable and this variable is linear. I have a hair on my face that I can't get rid of. It's tickling me. Okay. Alright, let's talk about the next method for graphing. I'm going to go backward for a minute. Here's brute force. Alright. Here is a method more appropriate if you know that you have a linear equation. And again, if it's a line, you really only need 2 dots to establish which direction it's pointing. Right? If you have a dot here and here, it has to be running this way. If you had a dot here and another one down here, hypothetically, then the line would be pointing this way. 2 is the minimum. And if you're going to basically do the same thing, insert an input into your equation and then hope it will spit out an output, input, output, like a little machine, all right? Then this is a faster method, right? Using the X and Y intercepts. Right. To that end, I have more recently drawn up this paper because it's just a little bit easy to read, perhaps. When you're trying to find what is referred to as the Y-intercept, which is probably the more famous of the two, right? What that entails doing is plugging 0 into an X. All right. Why 0? Because 0 is very easy, firstly. And if it's an intercept, it has to be on one of the axes, the point. All right. Let me erase this minimally, and I'll show you. Okay, good enough. Let me repair this like a good little ant. Right. Back on the lines there. That's close enough. All right. If you are going to employ method 2, which is using X and Y intercepts, let me just clarify that phrase first. An intercept, in general, is a point on either axis. So specifically, if we're talking about an x-intercept, then it's a point on the x-axis. If you're talking about a y-intercept, it's a point on the y-axis. Again, the y-intercept is usually the more famous of the two, but you could calculate them the same way. All right, you're just putting the number 0 in 2 different places. Let me put this aside for a moment and go back to a nice blank sheet. Where's this now? These triggers don't last forever. It's plastic triggers, especially if you put Clorox in the bottle. I'm not doing that, but this is rubbing alcohol that wipes this off. But it starts to crust, I guess, in the plastic joints. A little bit better than the eraser itself. Rickety, rickety, rickety rocket. Blast off. Okay. Make sure it's nice and dry. Good thing about alcohol is that it dries pretty quickly. I'm gonna screw up my markers too badly. Alright. Just to reiterate, this is method number 2. Alright, X and Y intercepts. Okay. If again, you're looking to calculate an X intercept versus looking to calculate a Y intercept, right, it is just inserting inserting 0 somewhat ironically into the other variable. It makes sense though. if you're going to find a dot that is on the x-axis, when an x-intercept would be on the x-axis, the y value would have to be 0 because it's neither up nor down, it's riding on the axis. If you are looking for a y-intercept, this is going to be on the y-axis. So therefore, you're going to stick 0 in place of x instead. All right. Now, as an example, I gave you this sheet. It's not necessary to use it, but it's kind of a scaffold. All right, I'll write an equation here for you. And then you could do the work here for calculating x-intercept, do the work here for calculating y-intercept, and then write the 2 points, right, that you would use to draw. Okay. So, a simple table. And if I press really hard, that works. Okay. Here's an equation. Here's our x-int. Here's our y-int. And here's our points. Should be x 0 and 0 y. Okay. If this is the equation, and it could be given to you in any arrangement. So let's say that you had it given to you just for the sake of an interesting problem, where the letters are on the same side. It doesn't matter if it's given to you that way or not. If you had to, you could employ algebra to shift the terms over. Right? The only time that you want to employ algebra realistically, right, is if you have to move stuff over equals. And it may or may not be necessary. Okay, so you are going to have the same equation twice. So I'll write it here and here. But you'll be putting your attention on different parts. Okay, now you see, as I tend to like to do, if again, looking for an x-intercept, I'm messing around with the y essentially. I purposely put this little pocket here because that's where the 0 is going, in place of y. And in this instance, when I'm looking for a y-intercept, I'm sticking a 0 in x. So I'm placing my little pocket here, and the 0 would be there appropriately. Okay. The advantage to using 0, of course, is that it eliminates that term. Why? Because how come? Right? 3 times 0 is just 0, which you don't have to write. It would be superfluous. What's left over then is this. 2x is equal to 6, which is a one-step linear equation. Right? Now you can employ algebra. Right? How do you justify moving 2 from here to here if you're looking to solve for x now? Now you must do the opposite operation. So if it's understood these two things pressed together are being multiplied, the coefficient times the letter, the opposite of multiplying is dividing, divide by 2 here, and for the sake of balancing it, be consistent, whatever you do to one side, do to the opposite side. Right. There's again a cancellation effect, which in this case will cancel to 1, which again is superfluous. You don't have to write 1. It's not wrong if you do, but it's unnecessary. This would be x is equal to the outcome of 6 divided by 2, which is just 3. Right. In this case, the value for x is 3. So that's one of our 2 points, 3, 0. And now we find the other. Similar process. To use 0 is super easy. All right. If you're adding or subtracting, it doesn't change anything. It's an identity. In the case of multiplication, it completely eliminates the term. 2 times 0 is 0. You are left with this. 3 times y is equal to 6. And you go through the same process, but now for the y variable. So, The opposite of multiplying by 3 is dividing by 3. The y's, pardon me, the 3's cancel to 1. Y is equal to the outcome of 6 divided by 3, which is 2. Therefore, your second term is 0 for the x input and 2 for the y output. Okay. 3, 0, and 0, 2. You can see that this is a little bit faster because you're not making 5 points. And again, as long as you know that you're dealing with a line, you don't have to make that many points, right? Unless you really want to. Unless you want to experiment. There's no sin in that. Okay, so I have to plot 3, 0 and 0, 2. All right. 3 is an x value, so from the origin you count 3 in this direction. 1, 2, 3 is positive. And if it's 0, it's neither up nor down, so you just place a dot there. Back at the origin to do the y-intercept, 0 is neither left nor right, but 2 is a y value and it's positive, so it's up. 1, 2. You have a dot like this. Right. And the end result is to just connect the points. To be a good sport, you should draw a line without scribbling or moving around. Use a ruler. Right. Why? Because this, without having to do any further calculations, you could figure out points in between, or you could figure out points beyond. Right? If you wanted to find a point here without a calculation, this is interpolation. If you wanted a point beyond, right, this is between known points. Linear interpolation. If you wanted a point beyond, this is extrapolation. This is beyond. Very practical in a science or business setting, right? Because you don't always have all of the data. Sometimes you just have, especially archaeology is another example of that. You sometimes have a sketchy, jumbled puzzle, all right? But you could make predictions, all right, based upon some established pattern. Right? You can make predictions based upon an established pattern. What kind of predictions? Interpolation is a point in between known points, or extrapolation, which is a point beyond the known points. Okay? Linear interpolation, linear extrapolation. It's kind of a cool thing. Okay? Anyhow, notice that you got a straight line again. How come? Because it wasn't really that, it was still a degree 1 problem. I know that it was written messed up, all right, by comparison. It was the original, here was the equation that I had just graphed, all right? If you analyze, it's usually the x specifically, all right? But if it were arranged in some other different way, notice that it's degree 1, and the same would be said for the y. If you had just in theory a 2 here, right, technically it would not be a degree 1, but it's usually the x that we pay attention to. Right? Degree 1s draw straight lines. Right? Something more complicated than that might make a parabola, or there's no name for that shape. If you had x to the third, the degree 3 equation, you kind of have the, I don't know how else to call it, but it's kind of like a drooping parabola, like staying alive, ha, 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 staying alive. All right, from Saturday Night Fever. Right. I have a weird imagination, right? I love what I do. I really do. And a person should. All right. Back to the sheet again. All right. Here is, again, as an overview of methods, a third method, which again, of all methods for graphing a linear equation, this is the go-to method, by hand. Even if you were using a graphing calculator, and 114 people, you don't have to have a graphing calculator, all right? Even if you did, though, all right, the calculator will require you to have something arranged in this style, otherwise known as the slope-intercept form of an equation. Famously, y equals mx plus b. All right, let's talk about this. All right. Get rid of this. This, so bear with me. Doesn't want to cooperate. Let's examine this. Let's see. If we explore method 3, right, which is graphing via the slope-intercept form of a linear equation, a line, famously y equals mx plus b. Just realize a couple of things. This is a model. Right. When you see this, the examples that you get, and let's see. Steal a good one here. Just hypothetically, if you had something like the problem we had done that was coincidentally arranged this way, we could have just zeroed in on two features. The coefficient of x, the thing that is sitting in the position where m would be, and the constant that is sitting off to the side, which should be sitting in the position of b, right? M and b are just labels, right? They're basically a job, if you will, right? In the model, right? And anything in an actual example, all right, that's sitting in those positions has those two jobs, right? This b is the weird label that we have for Y-intercept, which is why I say of the two intercepts, x and y, that's typically the more famous one. A natural question would be, why didn't they just call it y? I guess they didn't want to confuse it with this, because this y is going to be sticking around forever, right? Whereas this y value, right, the y-intercept, is really a coordinate. It's really an ordered pair of 0 always for the x, and then whatever the b value is. Okay, in this case it would be 2. 0, 2 specifically. That's a point, all right? This thing over here, all right, m, is the weird label for slope, right? I don't know. I can't say why we would choose, we, the math people of the world, all right, would have chosen m rather than S intuitively to represent the concept of slope. Perhaps since this is something that comes from the Renaissance period or just after it, all right, and they were still using Latin, and Rene Descartes himself was French, all right, perhaps in some other language, maybe French, maybe Latin, slope starts with the letter M, all right? That's just me seriously extrapolating, all right? I don't know, I'm making an educated guess here, all right? Anyhow, just read M as the slope and read B as the y-intercept whenever you see an equation sort of superimposed on the model like this, right? Save that model, y equals mx plus b, take your example and sit it on top of it so that it sits, you can compare the things sitting in similar positions. Thing attached to x, thing sitting off by itself. Okay? What's the slope? All right? The slope is the incline. We need to discuss that. It's the number used to express incline, right? Or you might say steepness, right? The pitch. And it's usually in the style of a fraction, right? What do I mean by incline? If you can imagine my arm here is basically a line, right? Depending upon the number that's sitting here, right? And it's usually a fraction, which means that this would be 2 over 1 instead of just 2. Whatever that number is affects how pitched the line is. In fact, if you had a negative, all right, it would be pointing down like this instead. Right now it happens to be in my, my example here is a positive, so it'll be pitched like this instead. Right. There's 4 possible slopes. So let me give you an overview of that. Here's what they would look like visually. Graphically, I should say. There's 4 possible slopes. So, very quickly, I'm going to just draw 4 T shapes, or cross shapes. That's my limited board space here. I really gotta get black here, because it's not showing up so good. Okay. Blood drive. Okay. And no more. Okay. Duly noted. That is a worthy cause. All right. I drew these 4 T's, cross shapes, I should say, to simulate a coordinate plane without pulling out the big board again. So I'm just going to be a good sport and I'm going to label them like this. Alright. If you have more or less the normal situation, or the situation that you're hoping for, not to corrupt your opinion, you would have a diagonal line that runs basically between the first quadrant and the third. That's really the only practical reason for right now to know the quadrant numbers, right? To give you an idea of what type of slope. Ignore the number for a moment. The sign is more important. This type would be a positive slope. Right? Granted, the line could be a little bit shallower, so you might have a line like this, or it might be a little bit more steep, so you might have a line like this. But in general, these arrows are stretching from the first, from the third to the first, or vice versa. All right? If, on the other hand, you have exactly the opposite situation, and you have a slope that is pitched downward like this, right, from the second quadrant down to technically the fourth, right, this would be a negative slope. If you are not doing a calculation, and there's a formula for calculating slope as well, we'll get to. If you're not doing a calculation, but you're merely staring at a drawing and you want to know something about the slope number m, all right, you could bet that it's going to be a negative if it's arranged this way. It again could be granted a little bit more steeply, like this, or a little bit more shallow. But if it's basically running from the second to the fourth quadrants, expect it to be negative. If it's running from the third to the first, or vice versa, it's positive. Right. This is a diagonal line, and this is also a diagonal line. Those are pretty much the two normal situations, and I would say I would favor this one, maybe just because I'm corrupted. Positive is good, right? There are these other two weird cases, though. Right. Let's say that you had something that was a perfectly horizontal line. And it doesn't have to be up here, but it has to be parallel to the x-axis. It could also be run down here, all right? In terms of the slopes, the way the calculation works out, this would be identified as m equals 0, right? 0 slope. Okay? You'll see in terms of the calculation that you end up with something like this. You get 0 divided by some number. And as long as that is the arrangement where the 0 is on top and the number is underneath, this means 0 divided by a number. That's perfectly fine. Right. If, on the other hand, you get a situation like this, I wish I had a darker marker here. Let's see if that works now. I'll have to put this in this. All right. If you had a perfectly vertical line, could be in either these quadrants or these, or even running on the axis itself, right? In this case also, it could technically be running along the axis. If it's vertical, in terms of the calculation for slope, right, m is undefined. A lot of times in the textbook they might say no slope, which I think is counterintuitive. All right? When you think of something as being seriously steep, and supposedly, you know, the slope term, number, is trying to quantify steepness, it would be kind of counterintuitive to say that it doesn't have a slope if it's perfectly straight up. But it's not pitched, right? It's not diagonal is really what it's getting at. So a better phrase, really, just not to confuse anyone, is to say that it is undefined, right? In terms of how the calculation would look, instead of having 0 divided by a number, what you would have in a situation like this is that you'd have some number on top of 0, which is the same thing as saying a number divided by 0, rather than 0 divided by a number. Okay, that is a mathematical impossibility, all right? That's why, and you could test it with your calculator, you get it undefined, all right? It would give you an error message, right, if you type in the numbers backwards. There's no commutative property of division, right? The arrangement of the pieces definitely matters, all right? It's undefined in this arrangement when you have a vertical line. Okay? Now, what's the formula look like? You've probably seen this before, but just to remind you, just to remind you, here's the formula for slope. Slope, otherwise mysteriously known as M, all right, is this calculation. In a fancy way, it's often written as a triangle Y sitting on top of a triangle X. This is the Greek letter delta. All right. Here's the logic. All right. If you see in any formula a triangle delta in this orientation pointing up, all right, delta. It's delta as in the letter D, and D as in difference, and difference as in subtract. Okay? So if you see delta Y, it means you're going to subtract 2 Y's. And these subscripts 2 and 1 here are just labels, they're not exponents. Right, it's just to say this is the second one, this is the first one. If you see delta X, then it means difference, subtract X's. So X the second minus X the first. Right? This is the fancy way of writing it. This is the practical way of writing it. All right? When you're calculating slope, know that it involves this. Basically, if you are given 2 coordinates, you could plug those numbers into this formula and it will spit out the fraction that is the slope fraction, the number that we use to express the pitch of the line. All right. You do have to take a little artistic license. My logic is basically this. If you have a number, an ordered pair given to you, and then a second one adjacent to it, do yourself the favor of labeling them. Just say that, oh, this is X to 1 and this is Y to 1. By sheer logic of, well, it shows up in my face first. Right? And if this follows it, let's call this X the second and Y the second. Again, subscripts are labels. They're not exponents. Okay? So you don't have to square anything. Let's do a calculation. The real reason for the triangle is because of the imaginary triangle that you could draw on a coordinate plane using these as endpoints of the diagonal. What would be a hypotenuse. All right. Anyhow, this is a good way to remember it. Delta, Greek letter for D in the English alphabet. D, if you like. D is in difference, and difference as in you subtract 2 things. So in theory, if you saw delta and then a happy face, all right, it would mean happy face number 2 minus happy face number 1. And think of how happy you'll be, all right, if you have to spend your Saturdays doing this. All right. Go team, go! All right. Yay, fun times with math. All right, Math World is a safer place than Corona World. All right, love Math World. Okay. All right. Let's calculate the slope. All right, given these coordinates, these ordered pairs, -1, -3, and 1, 5. All we need is this formula if we have these features. All right. Again, do yourself the favor, all right? Label this as X1, Y1. It's not wrong if you make this X2 and Y2, all right? But do one or the other. All right? Don't mix subscripts. These are the 1s, these are the 2s, or you can make these the 2s and those are 1s, whatever. All right? Then superimpose them on the formula. So if you draw the formula, just say hypothetically in pencil, right on top of this in something a little bit darker, all right? But it sits in the appropriate places. There's 4 voids that you're filling in, all right? And it's the seconds that you do first. So if this is Y the second, you're gonna appropriately plop a 5 here, okay? And that's starting to die. -3, right? Notice there's a negative in the formula, and this coincidentally has a negative in this number here. It's -3, right? So don't make the mistake of going, oh, that's enough. There's 2 of them, all right? X the second is 1. There's a negative in this formula, and this coincidentally is also negative. So I'm just going to write it like this. This is also fading out. Okay. If this is what the work ends up being, 5 minus -3, sitting on top of 1 minus -1. Remember, when you have a double negative, all right, it just means plus. All right? As long as they are immediately next to each other. It's like multiplication rules without really consciously thinking about it. I know this is a subtraction problem, but if there's no numbers in between the signs, join them that way. This does not look like a pleasant hand gesture, but, you know, 2 negatives make a positive, right? 1 plus 1. Okay. All right. So then you just do the calculation. What's 5 plus 3? 8. What's 1 plus 1? 2. All right. And then if you simplify this, you could treat it as if it was just ordinary fractions and divide by the GCF, right? The greatest common factor, which in this case would be 2. Or you could divide directly 2 into 8 and you're just going to get 4. When you are writing something for a slope, all right, it's somewhat preferred to be a fraction. Okay? Especially if you have to use it to actually draw dots. All right? This, remember, is a change in the y value. That's what the delta stands for also. Change in. That's the difference. All right? Change in y over the change in x. So if it's a change in 8, positive 8, it would technically be, and positive 1, what does that mean? It means literally that from the intercept, from the point of Y-intercept, not the origin, you're going to go up 8 because it's positive, and to the right, 2. All right. This is if you hadn't simplified it. Right? If you did simplify it, and that would be more ideal, the simplified version would be plus 4 over plus 1, which means up 4 and to the right 1. Incidentally, whether you use this or this, you're going to have the same exact slope. I know that it is suspicious looking because they're different numbers, but because they're presented in the style of a fraction, they're a ratio. That is to say, the relationship of the top thing to the bottom thing is identical, even if the numbers don't look the same. They have the same relationship in comparison to each other. This to this, this to this, right? The simplified version would be better. All right. Anyhow, positive means up for y, negative means down for y. This is the positive. Right? Positive means to the right for x, right? Negative would mean to the left for x. This is a positive, coincidentally. So it would be to the right. Okay? Let me draw a picture to reinforce this concept. I better erase this now. Remember 4 over 1. It's extra sticky today, eh? Thank you, rubbing alcohol. Let me pull this out of the way and then I'll put the other board back. And I'll plot those points on this coordinate plane. This I have to be a little bit more strategic. Little repairs here. Shoot me. Okay. If we were given these points, it didn't tell us to plot these, but I want to show you something that's interesting. If you did plot them, all right, you will see something interesting. All right, we had calculated the slope to be 4/1. Yes, you could just call it 4 if you like. In the equation that you might be given, you probably would just see the number 4 sitting in front of the x. If you're going to use it, stick a 1 under it. We got that from the calculation anyhow. This again means 4 up and 1 to the right. All right, from the Y-intercept, right? Not the origin. It's not a coordinate, the slope. It has a y value, a change in y, really more importantly, and it has an x value. But because it's not officially a coordinate given to you in parentheses, the comma in between, it's in the style of a fraction, you can't really treat it like a fraction. You can't really treat it like a coordinate. So don't go to the origin and start plotting, all right, using this. If you're gonna plot dots, from the Y-intercept, all right, for slopes. Okay, now this point, -1, -3, -1, 1, 2, 3. There would be a dot here. This 1, 1, 5 over 1 up 5, 1, 2, 3, 4, 5. There would be a dot here. If in theory you drew a line connecting them, I'll try to do that nice and neat, purposely overextending this line, like that. I don't really have an equation, but I don't technically need one. If you do this on graph paper, what you could do is get the same slope without doing the calculation. That's the advantage of doing it visually, graphically, all right, versus algebraically, all right? Remember what I was saying before about deltas? If you can imagine a teeny tiny little triangle that would be connected like this. I'm going to try to make it very faint. All right. As long as it's on a grid, you could count the boxes. How many boxes wide is this? I'm going to put dots to kind of make it easy to see. It's 2 boxes. All right. How many boxes tall is this? One, 2, 3, 4, 5, 6, 7, 8. It's 8 boxes. It's good to know how to do this via the calculation because oftentimes you don't have graph paper. But if you did, all right, as long as the coordinate plane is nice and even like this, all right, you could just stare at the picture and get the same information, right? Delta, delta, all right? Delta triangle, delta triangle. It's an imaginary right triangle, all right? And depending upon the slope, truly, it might be pitched very steep or more shallow or somewhere in between, all right? The only downside to doing this visually is that you would not get a sign, right? The algebra, the calculation, right, gives you definitively a negative or a positive, right? This is another reason why you try to memorize those four situations, right? If you could say to yourself, well, this is very steep, but it's basically running between the first and the third quadrant. What kind of slope is this? It's either positive, negative, zero, or undefined. A situation like this would be a positive slope. It's positive, all right? What would the numbers be? 8 and 2, technically, but that simplified is 4 over 1, which is just 4, right? So when you're writing an equation, you use the number 4 for the sake of simplicity in the equation. When you're drawing it, you use the simplified fraction. Incidentally, this is why the relationship would be the same. The ratio of 8 to 2 is the exact same relationship as 4 to 1. It's just using different figures, all right? A smaller right triangle would fit in here. Let's say that you connected this and this, all right? 1 block, 1, 2, 3, 4 blocks, all right? And then you'd see a second right triangle. 1 block, 1, 2, 3, 4 blocks, all right? This triangle would be like this into infinity, all right? That steepness is going to be the same consistently. Okay? It's just using smaller figures to express the same slope. Okay. All right. Moving on. Having said this, now we can get to graphing much more efficiently. Are we on time? An hour 23. Right. If you look at this last page from the packet, well, second to last almost. This explains a lot of the same information I was just talking about. All right. This is the slope-intercept form of a line, y equals mx plus b. This is a scaffold, basically, to get you to zero in on that piece of information. The y-intercept of the two you want first. And it's the easier one to identify. Whatever number is sitting here, make it the y component of the ordered pair. The x component will always be 0 because it's a y-intercept, right? Meaning it's sitting on the y-axis, that dot. All right. From there, you could generate an infinite number of points. All right. It's just that, somewhat ironically, the slope, if it's given to you, or if you calculated it, all right, it has to be understood as not being a coordinate. So you're not going to the origin when you find this. All right. You'll pluck it out of whatever equation that you're given, but you're going to read it like so, and you're going to plot from the y-intercept. So here's another example. All right, so to simulate my table here, y, I should have a nice nice markers. Y equals mx plus b. No, would be right, left. Okay. Positive up, positive right. Negative down, negative left. If you were given this unique equation, example, 4x minus 3y equals 9. What you want to do in this case is strategically rearrange it via the process of algebra, opposite operations, to get it to more closely resemble the model. So you notice in this case that you have the x and the y, and they're sitting on the same side of the equals. You want to basically just move 4x, this term, over to the opposite side first. So how do you do that? Well, I'm going to throw this marker out. What is the sign of this x if it's not written, this 4? You could assume that it is positive if it's not written. So if you wanted to justify taking the whole chunk from here and plopping it on the opposite side, even if you can't combine it with 9, it's okay. The opposite of plus is minus, so we're going to subtract. Bring the letter with it, right? Strategically park it over here on the opposite side of this x, right? I don't know what x is, granted, but I don't need to. By sheer logic alone, something, even something mysterious minus itself, cancels out of existence, right? So this goes away. Then you're left with this, negative 3y equals, to make this conform a little bit more closely to the model, I'm going to put the minus 4x in front. It's not wrong if you put the 9 in front. Intuitively, you might do that just because 9 is on top here. No sin in that, but we want to make it resemble the model as closely as we can. Just make sure that the signs are appropriate. If this is a negative, then that's minus 4x. Right? If there's no sign here, that's plus 9. Right? The next step is to move the coefficient of y, right? Because in the model we don't have that. So the opposite of multiplying is to divide by 3, negative. And then be consistent. Don't just do it to one or the other, do it to both pieces. Each term gets divided by that same 3. Right? Whatever you do to one side, do to the other side entirely. All right? There's a cancellation effect. The 3's cancel and they become 1. A negative divided by a negative is a positive. Right? So that will virtually happen all of the time. So what you're left with is what you want, y equals, right? The same thing here. A negative and a negative, you end up with a positive. So if you want, you could just put plus 4. And this fraction, even though it's improper, you want a slope to be in the style of a fraction because then it's easier to use, right? So I'm just going to leave it like this for right now. It's more concisely written as 4/3 x. If you're going, this is a side note, if you're worried about where the letter x goes, it is always technically attached to the top. But because we're using it in the way that we are, all right, just kind of separate it out. All right, you're really just paying attention to these numbers here. All right, if you're going to attach a letter to anything, it would technically be on the top. Then there's this little calculation here. All right, this is division. All right. And it's the integer rules for multiplication division rules, right? So one of each means that you have a negative overall, and 9 divided by 3 is just 3. This is the original example rearranged to resemble slope-intercept form. Why? How come? Because this is the most practical form if you have to do any of this graphing by hand. Right. So now we're going to pluck out the appropriate pieces of information. Kind of stretched over here. All right. What's sitting in the B position now? The 3. If B is sitting, negative 3 is sitting in the B position. Yeah, I know it's positive in the model, it doesn't matter, it's negative 3 in real life. Then write this as this coordinate, negative 3, this ordered pair. What's sitting in the M position? This fraction, even improper, is still considered ideal. So M is equal to 4 over 3. Right? If it makes it a little bit easier, put in the superfluous information that is not really necessary. That is, put in the signs. Right? If you have a positive fraction, then what you could say is that this is a positive on top and a positive on the bottom. All right? Which means what? It means move 4 up and 3 to the right. All right? From the Y-intercept, not the origin. It's not technically a coordinate in spite of its similarity. It's not an ordered pair in spite of its similarities, because it has x's and y's involved in it somehow. All right? So you got to be careful. All right? It's from this point, which is why I put it first. This is the more important thing. You start here. All right? Then you could generate an infinite number of dots without doing a calculation. You should just keep going up 4 over 3, up 4 over 3, up 4 over 3. All right, I'll do that now. Remember these numbers, I gotta move this. Just have to drag out my thing here. Never good when you have noises off camera. It's like, I don't know what happened to him. He died in the middle of the video. Well, yay, that's the myth. And all that personify it, right? Sorry, I'm just trying to be funny. Oh, God. Yeah, that's horrible. All right, down this way. Like straight lines, and that's kind of crappy, but I'm not going to change it. Just wasting too much time. All right, so what do we have? We have our Y-intercept, which is 0, negative 3. Let's make sure that that's correct. Yes. And we have our slope, which is 4/3. All right. So again, you plot the Y-intercept first, always. Okay. So at the location of 0, negative 3, 0 is neither left nor right, but negative 3 is down 3. So 1, 2, 3. You would put a dot here. Okay. And again, from this point, right, not the origin, you're going to go 4 up and 3 to the right because of the signs. This is a positive and that's a positive. Right. So, because again, it's not a coordinate, you have a little bit more freedom. You know how when you're plotting coordinates, you absolutely must do the x portion of this first. Right? When you're using a slope, right, the y portion of the x portion of it, it doesn't matter which you do, you're going to land on the same line. All right, I'll do it both ways. I think my instinct, and I don't want to corrupt you really, my instinct is to just do the 4 first because it's on top, right? But it doesn't actually matter in the case of the slope. So from here, 1, 2, 3, 4, resist the temptation to make a mark until after you move the x, and then go over to the right 3, 1, 2, 3. Even if I did, again, the x portion of this first, I'm going to land in the same place. All right, 1, 2, 3 to the right, up 4, 1, 2, 3, 4, same dot. And the beauty of this is that you could generate an infinite number of dots, and in theory, if you compensated, back the other way as well. So if you want, you'd only need minimally 2 if you're doing a straight line, but if you wanted to do, you know, several of these, keep doing it. Up 4 over 3, make a more pronounced dot. Up 4 over 3. 1, 2, 3. Okay. And then draw a line through them. In case of an actual line equation, I will actually use a rule. Overextend backward and forward. Okay. Now, when I was in school, not too long ago, they used to make us do this by hand a lot more than there were graphing calculators when I was in college, but especially in the algebra classes or the pre-calc classes, they tended to make us do things by hand. So let me impart one piece of wisdom to you. When you do this by hand, you might do several equations on the same page, the same coordinate graph paper. So to distinguish one drawing from another, write the equation along the line that you draw. So for example, if this was originally 4x minus 3y equals 9, a good little math geek, all right, would write the equation along that line. I'll use different colors to distinguish things. It's also helpful. All right. You could write it in the way it was given to you, or you could write it in its rearranged form. This is a little bit easier for another person to interpret if they saw it in its slope-intercept form instead. They go, ah, yes, naturally, because why? That is that point, all right? And the incline of over 3 up 4, over 3 up 4, over 3 up 4 is consistent. This imaginary slope, this imaginary slope, this imaginary slope, forever and ever and ever. Okay. I'm just going to mention some terminology. Outside of math world, where we live, right? I should put this over here. The only real difference is that they changed the labels a lot. You know, depending upon the circumstances, to match whatever their experiment or business model is, a person will change the labels from X and Y to, you know, maybe time and money. You know? As long as it's a 2 variable situation. So let me give you some summative information here. All right. When you are writing an equation, if you have to from scratch, writing a line equation anyhow, here's some information that would be good to know. Expect one of 3 situations. All right, I need red. You could have more or less the normal situation, what you would expect, which is a diagonal line. When you have a diagonal line, the equation model that you're going to borrow is this. The slope-intercept form. It has both variables present, both letters. if you have something a little less complicated, the equation is less complicated. So for example, if you had a horizontal line, it's a dumbed down version of this. All right, the equation will just be y and then some number. The other features are not included. It's just y. It doesn't include an x for a horizontal line. It's just y and then whatever the y coordinate would be. Basically, whatever number is given to you in the coordinate, that's the number. And since you know for horizontal lines the slope is 0 anyway, right? That's why there's no term that involves x. Right? So just use this simplified equation. The x values could be anything this way and anything into infinity this way for a horizontal line. And if you have the last situation, a vertical line, it is also a slimmed down version of the line equation. Right? It's basically, this is wet still. Geez, that took too long. It's going to be x equals some number. Usually what that means is if you have a coordinate, it's whatever the x value is. And you're going to have 0 in theory for the y value. You probably just have the x-intercept. In a vertical line situation, remember the slope is undefined, right? Y, which is the how come. English gets you in trouble, right? Because of the ambiguousness of the phrase y. All right. The y value in a vertical line could be anything. All right. It goes on into infinity up and into infinity down. So it's not specified. The equation is this slimmed down, dumbed down version of the line equation. It's just x equals some number. Horizontal line similarly, y equals some number. The only time that you see both variables in the same equation is if you have the normal situation, a diagonal line. But these two, you probably just know the y-intercept or the x-intercept. Okay. What happens outside of math world is that they just change the variables to the specific application. Nonetheless, the relationships are the same. Here's kind of a generalization as well. I'm not going to erase this. I'll just sort of put it here above this. There's a more general phrase. These are some terminology that are good to know. If this is, again, the slope-intercept form of the line equation, y equals mx plus b, because of the arrangement of this, where you notice the more interesting stuff is happening all on the right side, where the x is. This is the dependent variable. You could rearrange the equation in theory so that y has the more interesting parts. would change its purpose, basically. But in the normal situation, where y is rather lonesome on one side, it is generally referred to as the dependent variable. Right? It depends on this gobbledygook in order to decide what it is. It's noon, or else the bells would not be ringing.
Hallelujah, it's math!
Yeah, I know, I'm gonna get fired for being snotty, right? Anyhow, the x, because of the way it's situated, it's the independent variable of the two, right? Its identity is not dependent upon y. Y is dependent upon x because of the features that are attached to it and adjacent to it. Right? All right. Think about it this way. X effects, if that's the correct spelling, I think it's affects. Y. Right? In this case, you might say it this way. Y is dependent upon x, but not the other way. Vice versa. At least according to this arrangement of y sitting by its lonesome. Okay. Here's another analogy. Right. Math world has decided, I'll put this here, that there are 1, 2, at least for right now, outside of calculus. Math world is 4 quadrants, 1, 2, 3, 4. The real world, which is adapted from math world, and math world is a theoretical situation. The real world only pays attention to, or primarily pays attention to, just 1 quadrant. That's why a lot of times when you see some standardized tests that you've taken in your life, the graphs are no more complicated than quadrant 1, right? They don't even label it, right? But the real world applications, right, tend to limit the scope to just the first quadrant, right? And they change the labels, right? Instead of calling it X and Y, they'll call it whatever is unique to the problem. This is still nonetheless the axis of the independent variable running this way. And this is the axis of the dependent variable running this way. Right. If you are in MAT-114, this is where we part ways, right? Because you're not really responsible for the thing that follows. If you're on 114, what I'd like to do with you now, and if you're in 090, you can stick around, it's up to you. I want to go through this word problem that I gave you because it's a real world example where they changed the labels. Still using the same model. So if you have this, print this out, you MAT-114 people. These fumes are starting to affect me a little bit. Rubbing alcohol, very potent. And it works. Gets the ink off better than just rubbing. let's discuss this. All right. This page. All right. MAT-114 word problem. Javier owns a business that sells bicycles. I stole this from the textbook, by the way. He believes the profit or loss from the bicycles sold can be estimated by this formula. Now, what I want you to notice about this is that there are two letters. They're calling it P and they're calling it S, but it still resembles the shape that we're familiar with. The model. Here's the math world model. Y equals mx plus b. And here's the real world application. P is equal to 60s minus 90,000. Just make sure that you realize that these are performing the same function, the same job, right? What is x in the model is called s here. This is the independent variable. What is y in the model is called p here. This is the dependent variable. And therefore, this is what would normally be the y-intercept, but they're just going to call it instead, unique to the problem, the p-intercept. And this is the slope. So if you had to graph it, you already could. Right? You just have to identify what jobs are being fulfilled by what letters and what numbers. Okay. Now it goes on to specify S is the number of bikes sold, right? And P is presumably a dollar value, at least in the United States, right? So it's profit, right? In theory, it could be a loss though, right? Now the first thing is to graph this, right? Graph this function, a linear equation, P equals 60s minus 90,000 for this situation. Let's see, A. We're going to attempt to graph this by hand, right? P equals 60s minus 90,000 for the situation of bikes sold being less than or equal to 5,000 bikes. Okay. Now, by hand, it doesn't have to be perfect. Try experimenting with larger increments. The whole point of this exercise is just to get you acclimated to doing something by hand. Again, you normally would use software, you'd use a calculator, but don't be intimidated by the size of the numbers. And as a matter of fact, and I'll show you my original sketch of this, when you first start drawing it, you do it badly, right? Because you're still trying to feel what the increments ought to be. So go through the experience just simply to have the experience, right? It's important you learn something from it. All right. We already have some information here that's useful to us, right? If this is 90,000, negative 90,000, is sitting in the position of B, the y-intercept, then this represents a coordinate that would be well off the scale of a normally incremented coordinate plane. It's okay, right? What this is telling you, right, 60 sitting here in M, is that there's a relationship of 60 to 1. This is 60 up and 1 to the right. From that point, technically, right? That's in the ideal situation where you have an enormous piece of graph paper, all right? So you're going to worry less about that. The one thing that they gave you as sort of an advantage here is that they told you this much information. This, in a very subtle way, is telling you the scope of this graph, right? This is basically, think of it as being, this 5,000 as being a maximum, all right? Since it's an S, it's really an X value. A maximum along the X-axis. We're just calling it the S-axis in this case. So remember, we're going to narrow our scope from 1, 2, 3, 4 quadrants, that's math world, to just ideally this one. And because of the nature of this point, negative 90,000, maybe this one. So for right now, our graph is going to look probably like this. All right? And as far as how long along the x-axis we're going to be, it's going to be 5,000 or less to the point of 0. Right? That's what the increments will have to be, along the x-axis at least. All right? Let me move this out of the way, and I'll put the graph paper back. My edge is too shallow. So if you start with a fresh piece of graph paper, let's say that you start with something like this. You have a horizontal axis. We're probably not going to need this much of it, but I'm going to purposely scoop this over to the vertical axis over to here. Sorry. Oh, killed me. Right. I'm going to purposely narrow our focus to what would technically be the first quadrant and the fourth quadrant. All right. You don't, what's kind of hard to sort of undo, I'm trying to think of the correct phrase. We're kind of brainwashed to do things in a certain way. We have conditioning, right? So you might go, this increment and this increment on the horizontal and the vertical has to be the same. That's the ideal situation. But think of all of the graphs that you've seen in standardized tests. Were they ever that nice? Not in my experience. They would have increments here, right? That is, each block is equal to a certain amount. That would be totally different than the way that it is vertically. So if standardized tests can get away with doing that, so can you. Right? So if they've told us that our increments are 5,000, all right, let's just, because it's visually pleasant, maybe make an increment of 2 blocks, and we'll call that 1,000. I'm just going to cheat and call it 1K. And then I'll be consistent through it, and I'll call this increment here as another 1,000, which would be 2K. And then another 2 blocks would be 3K. And another 2 blocks would be 4K. You do have to be consistent along an individual axis. And then there's 5K here. All right? But my real point is, I'm taking a lot of artistic license, right? And you don't have to feel guilty about it. All right? It doesn't, you're never gonna have a piece of graph paper that's gonna, that each block is gonna be the unit of 1, and you have enough blocks. So you break it down into larger increments. Okay, so 1,000, 2,000, 3,000, 4,000, 5,000. And again, I've only based it on that as being this imaginary maximum here, this wall, right? Because that's what the instructions said. The S value is less than or equal to 5,000 bytes sold. And this, which is normally our x-axis, is being called our s-axis instead, which represents bytes sold. Okay, so if you want to even chop it off at this point and call this s, that's cool. All right. Now, let's plot the only point that we have. This first piece of information is cool. The second piece of information is that we know what the Y-intercept normally is. And in this case, we're just alternatively calling it the P-intercept. This is the p-axis now, all right, instead of the y-axis. We have determined that we have this much information. Now again, because this is a large number, 90,000, you're never going to have a piece of graph paper that's sufficiently, one block is 1 unit, and that you're going to have 90,000 of them down here. It's just not going to happen. So what you have to do is decide, and you only know from playing around with it, all right, what the increment ought to be, right? So if you dig, I know this is kind of just skipping around a little bit. One of the questions is going to ask you to do a calculation for a dollar value, profit, of 150,000. What that means, and it's kind of cheating because I'm looking a little bit further down the pike here, all right? That's basically the maximum of the drawing, all right? So 90,000 and 150,000. That's dealing with, and I know this is kind of stretching a little bit, but in my mind, here's what I'm thinking. 90,000 and 150,000. If you just pay attention to the non-zeros, are the numbers 9 and 15, all right? The number 9 is made of these factors. The number 15 is made of these factors. What's the greatest common factor? 3 is the GCF, right? Now, let's tack on some zeros onto that, all right? If we want the first block, all right, the first increment along the axis to be useful, all right, let's put it in the magnitude of the order of 10,000. So let's say that it's, instead of 3, we're going to call it 30,000. So perhaps this, and it's totally arbitrary. Anybody could have decided what they wanted, really. I'm going to make this increment 30,000, right? Notice that the scale is way off, all right, compared to this. This is just 1,000, 2,000, 3, 4, 5. And I'm just using K's not to put zeros there, all right? This being down is 30,000. I'm going to be consistent now. If I've just decided arbitrarily that 2 blocks is that increment of 30,000, then another 2 would be negative 60,000, and another 2 would be negative 90,000. I know that it's hard, all right, and not to belabor the point, that you're like, wow, how did you decide that? You only know by playing around with it, and it does help to be strong, all right, in some fundamental ideas like factors, all right? You learn from doing it a lot, right? This took me many years of my life to sort of get used to, right? So don't be intimidated, right? Anyhow, do be consistent along the individual axis. I've decided that 2 blocks is 30,000 arbitrarily. Good, all right? Do it up now. Here's another 2 blocks. 30,000, 60,000, 90,000, counting by 30s, right? I know that's weird, but it works. 120,000, 150,000. And again, I've only chosen that as my ceiling here because the problem eventually will ask for that. Don't be afraid when you're doing these types of problems to read the whole problem first. You know? P. All right? Basically, this is all I need now, all right, in order to draw this graph. The hard part is over. I'm going to take this coordinate, 0, negative 90, and just replace 3 zeros with a letter K, and put a dot at that location. It's a Y-intercept that we're just calling it a P-intercept instead, meaning this axis. There's a dot here. Okay. Now, let's cheat, all right? Let's do a calculation for the X-intercept. Nobody asked us to do that. All right, but we know from having talked about these earlier methods for graphing, right? Either brute force generating an infinite number of dots, at least 5 in this case, X and Y intercepts and the slope intercept form, they gave us this. But to draw a second dot
to help us establish this picture. And the whole point of a graph is so that you could read it, all right? Let's cheat. Let's go this way. We have technically a y-intercept already. Let's calculate an x-intercept, a dot that in theory would run along here. If I calculate an x-intercept, which again, we're just going to call it an s-intercept, all right? That means that the y value, which is really going to be called the p-value, is just going to be 0. So if this is the formula, P equals 60s minus 90,000. And we take advantage of intercepts as in using 0 somewhere. All right? Let's just put a 0 here, all right? And then rearrange the parts. All right? I'm going to move the 90 from here to the opposite side of equals. How do I do that? Opposite operations, right? So what's the opposite of subtracting? Add 90,000. Cancels. I'm sorry that that's very faint. It cancels. It's a little bit better. And I'm going to plop it over here. And it's positive on this side, right? 0 plus 90 is just 90. Equals. And then there's this 60s here. All right, because I'm running out of space, I'm just going to kind of write the work here. 60s is equal to 90,000. I just have this weird sort of idiosyncrasy. I like the letters to be on the left side. It's okay if you keep it like that. As long as they're on opposite sides now and the signs are appropriate, it's all legit. How do I get rid of 60 if it's being multiplied? Divide by 60, cancels here. Divide by 60. You could use your calculator or you could do this brute force, right? Here's a trick. Pairs of zeros would cancel. The relationship between 90,000 and 60 would be the same as if you divided 9,000 and 6, all right? 6 goes into 9 roughly once with 3 left over. 6 goes into 30 exactly 5 times, all right? And then it's just 2 extra zeros because I didn't cross off anything else. The bottom line is that the S value, whether you divided 90,000 by 60 or 9,000 by 6, same relationship, is this, 1,500. Okay, so my x-intercept, since this is really s and then p as opposed to x and y, is 1,500 at the point of 0. Along this axis, I'm going to put a second dot. And the second dot is going to be in between, if this is 1K, it's really 1,000. And this is 2K, and it's really 2,000. Exactly halfway. Because if it's 1,000, right, then this point right here, exactly in between them, would have to be 1,500. Okay? That's kind of the reason why I made it 2 increments each, right, to get it kind of a middle. But again, that's only something that I knew to do from a lot of years of experience, so don't be dissuaded. Here's my original drawing, all right? I want to show you what my original drawing is. It's a mess, all right? It's correct, but it's sloppy, all right? Why? Because I was experimenting. So never feel bad if your first attempt at this is kind of crummy, all right? What you do is you whittle it down into the bare essential. I'm doing it a couple of times. Anything, math, some other subject, all right? The more that you do it, the better you get at it. All right? Anyhow, here's essentially my x-intercept and my y-intercept. We're just calling it an s-intercept and a p. I only need 2 dots. This is definitely a linear relationship. That's what this section is. So what I'm going to do is I'm going to draw the line connecting them now. And I am going to purposely overextend this line both ways so that it looks like that. In theory, business is good and this is profit is going up. Okay. Now, here's what we can do. we can answer the questions. If the original question was, and I'll point at it again here. The original question, part A, was to graph this, all right? Using the little bit of information that I had. Kind of narrow your focus. Like, I hate to say this because I hate horse racing and I don't think it's nice to the animals, all right? But in horse racing, what do? They put blinders on the horse. Why? To keep them focused on what's ahead of them. Do that in your own case, all right? I know there's a lot of gobbledygook going on here. I don't want to erase it because I may have to point to it. What I want you to do is now narrow your focus to basically what you see encapsulated by this circle, because that's really what you're going to need in order to answer the questions. We did the hard part, we graphed it, all right? What's the practical usage of a graph? The graph can give you information, there's my little groundhog friend, all right, without having to do any more calculations. You've done it already, all right? I'm going to extrapolate. I'm going to get the value of a point beyond the known points, all right? So in this case, part B says, from the graph, this green thing here, estimate the number of bicycles that must be sold for the business to break even. This green thing. Estimate the number of bicycles that need to be sold to break even. If you break even, all right, it's not a technical term. Think about it in vernacular usage. It means it's neither here nor there. Neither made money nor lost the money. It's zero, all right? We already technically calculated it, all right? But the break-even point would be right there, all right? This is where a person breaks even in a business like this. The profit is neither positive nor negative. This is $0. So, how many bikes would need to be sold in order to be $0? We already did the calculation. You would need to sell 1,500 bikes. Here's some summary of information I'll put here now. Part A is to graph it. Part B is to calculate where you break even. Break even means $0 in profit. What does that mean? It means sticking a 0 in place of P in this calculation, which is essentially finding the x-intercept. Which we're just calling S-intercept. So the number of bikes to make $0 in profit but not lose is 1,500 bikes. Okay. Now, the more interesting question is part C. Okay, this in black here. From the graph, estimate the number of bicycles sold if the profit from selling bicycles is about 150,000. Basically, this is drawing connecting lines here. If you can imagine, get this out of the way for a moment. 150,000 is up here. And that's right on the grid line. What does that represent in terms of a dollar value? A number of bicycles. 4,000, right? Because this $1,500 in profit is connecting down vertically to this 4,000 bikes. That's the answer to C, right? 4,000 bikes is on par with 150K in profit. Okay? I can't stress it enough. You're never going to have graph paper that's going to fit every situation. So don't be afraid to take a little artistic license with the increments, right? And it may take a couple of tries. It took me at least 2 before I got a nice, comfortable sort of medium, if you will. Okay? All right. That's it. All right. As I said, I'm at 2 hours and 15 minutes here. Section 6-7, don't worry about it because I'm just going to do it on Wednesday. All right. And if I need to make up for lost time, I'll make a video for Friday. All right, or worst case scenario next week. I don't really want to do that. Anyhow, just try the section 6-6 homework. Those of you in MAT-114. Okay. All right. I'll see you on Wednesday. All right, and you folks that are maybe in 090, you'll see this probably at the end of the week anyhow. Okay. Take care. Be careful out there.